All right, let's get into it. We are constantly surrounded by sound, right? Music, talking, just the general noise of life. But have you ever stopped to think about what sound actually is? Well, today we're going to pull back the curtain and break down the physics of sound, all the way from a tiny vibration to a massive sonic boom.
You've probably heard this one before. It's that classic philosophical riddle that kind of messes with your head, blurring the line between what's real and what we just perceive. But honestly, it's the perfect place for us to start.
So, what do you think? Does it? Well, if you ask a physicist, the answer isn't some vague philosophical maybe. It's a clear, definite yes, absolutely. That tree for sure makes a sound, whether there's an ear around to hear it or not.
And here's why that's a definite yes. In physics, sound isn't about the act of hearing. It's a physical event. When that tree smacks into the ground, it creates a physical disturbance, a wave of energy that shoots out through the matter around it. The air, the ground. That disturbance is the sound. It's a real thing that exists all on its own.
Okay, so we've got this disturbance, but how does it actually get from that falling tree all the way to your ear? Well, let's follow the journey of a single sound wave.
Here's the most important thing to remember. Every single sound in the universe, no exceptions, begins with something vibrating. Seriously, think about it. A guitar string being plucked, a drum head being hit, or even your own vocal cords when you talk. It all starts with that little back and forth wiggle.
And you can see exactly how that wiggle turns into a wave. As something vibrates, say it moves forward, it squishes the air molecules together. That creates a little pocket of high pressure, which we call a compression. Then, as it moves back, it leaves behind a space with fewer molecules, an area of low pressure we call a rarefaction. So that vibration just keeps going, push, pull, and that creates this repeating pattern of high and low pressure zones that travels outward from the source. This moving pattern is the sound wave. If you look at the graph, it's super clear. The peaks are those high pressure compressions, and the valleys are the low pressure rarefactions.
But of course, not all sounds are the same. A whisper is obviously different from a yell. A high note on a flute sounds nothing like a low note on a bass. Well, all those differences boil down to three basic properties of the sound wave itself.
Let's start with speed. And you've all experienced this, right? You're watching a fireworks show, you see the big, bright explosion in the sky, and then a second or two later, you hear the boom. That's because light travels insanely fast. But sound, well, it takes its time. That delay you notice is just the time it takes for that pressure wave to travel all the way from the sky to your ears.
But here's the thing. The speed of sound isn't always the same. It totally depends on what it's traveling through. Just look at this chart. Sound moves way, way faster through denser stuff like water and steel than it does through the air. This is the whole reason you can hear a train coming by putting your ear to the metal track long before you can hear it chugging through the air.
Okay, so on to the other two big properties, pitch and loudness. Now, you might think they're kind of related, but in physics, they're two completely different things. Pitch, how high or low a note is all about frequency. That's how close together the waves are. Loudness, on the other hand, is about amplitude, how tall those waves are. This little cartoon explains it perfectly. The quiet bird is putting just a little energy into its chirp, creating a gentle wave with a small amplitude. But the shouting bird, it's putting a ton more energy into its vibration. That creates much bigger pressure changes, a wave with a much greater amplitude. And our ears hear that bigger amplitude as a louder sound. Simple as that.
So, we've tracked the sound wave as it zips through the air. But how does that physical pressure wave get turned into the actual experience of hearing something inside our heads? Let's follow it on the final leg of its journey, inside the human ear.
The process of hearing is this incredible mix of mechanics and biology. So first, the sound wave travels down your ear canal and smacks into your eardrum, making it vibrate. Then, those vibrations get passed along and made even stronger by three of the tiniest bones in your body. And finally, they arrive at the inner ear, the cochlea, which is where the real magic is about to happen.
This part is just mind-blowing. The cochlea is this little snail-shaped thing filled with fluid. The vibrations make waves in that fluid, and those waves cause thousands of microscopic little hairs to bend back and forth. That bending motion is what finally converts the physical energy of the sound wave into an electrical signal that gets shot up to the brain. And just like that, a pressure wave becomes a memory, a song, or a warning. It's just amazing.
Now, things get really, really cool when the thing making the sound is actually moving. This is where we get some pretty familiar and sometimes super dramatic effects that I guarantee you've heard before.
You know this sound instantly.
That high-pitched meow as an ambulance or a race car speeds past you. That distinct change in pitch as it approaches and then moves away. That's a famous phenomenon called the Doppler effect.
So to understand what's going on, let's start simple. Imagine a car that's just sitting still, but its horn is blaring. The sound waves spread out from it perfectly evenly in every direction, like ripples in a pond. No matter where you're standing, you hear the exact same pitch.
But now, watch what happens when the car starts moving. It's basically chasing its own sound waves in the direction it's heading. This causes the waves out in front to get all bunched up and compressed, while the waves it leaves behind get stretched out. And that's the whole secret. For you, standing on the sidewalk as the car comes towards you, those bunched up waves are hitting your ear more often, a higher frequency. So you hear a higher pitch. Then as it passes and moves away, you're getting hit with those stretched out waves less often, a lower frequency, and you hear a lower pitch. That's it. That's the Doppler effect.
So that leads to a wild question. What happens if an object, like a fighter jet, goes so fast that it actually breaks through its own sound waves? At that point, the pressure waves in front of it can't get out of the way. They all start piling up on top of each other, building up into one single, massive shock wave of pressure.
And when that huge wall of pressure passes over you on the ground, your eardrums get hit with a sudden, massive change in air pressure. And we hear that as a huge boom, a sonic boom. And you can see here, because the jet is literally outrunning its own sound, you don't hear the boom until after the plane has already gone past you.
You know, all these principles aren't just for jets and ambulances. Nature figured this stuff out a long, long time ago. Animals like bats and dolphins use something called echolocation. They send out little clicks of high-frequency sound, and then they listen for the echoes. By interpreting how those echoes bounce back, they can build a perfect mental picture of their surroundings to fly or swim and hunt in total darkness.
So from a simple falling tree all the way to a bat's amazing sonar, sound is this deeply fundamental part of our physical world. And we humans have learned how to use it in incredible ways, from sonar that maps the deepest parts of the ocean to medical ultrasounds that let us see inside our own bodies. It really makes you wonder, now that we understand the physics behind these simple vibrations, what's next? What else can we do with sound?